Now let us consider some of the important factors which affect the chemical shift. Okay. Now let us take these examples. Here you have the chemical shift for the sp2 hybridized carbon at 127.4, 127.4 because of the symmetry. Okay, you have a plane of symmetry here. So this carbon will resonate at same field as this carbon. Okay. Now when you put a substituent here, that is when you put a carbonyl, there is delocalization of the pi electrons towards the carbonyl. Okay, so by delocalization, that means that this carbon now will be positively charged, and you will have the double bond here. Okay, now this carbon which is positively charged, that means then there is less electron density, or we can say that this carbon has been deshielded, so it will resonate at a much higher chemical shift value. Okay, so from 127.4 to 150.7. Okay, and now about this carbon, see, from 127.4 to 129.3, it's because of the electron withdrawing nature of this carbonyl. Okay, so from 127.4 to 129.3. Now the other case we consider here is the lone pair with the lone pair on nitrogen, which can be delocalized towards the pi bond. Okay, now this carbon which earlier here it is deshielded, here it has been shielded. Okay, so from 127.4 to 193.0. Okay, and this now has been deshielded because of the nitrogen atom, because of the minus I effect of the nitrogen atom. Nitrogen is more electronegative than carbon, so it withdraws electron density towards itself, so minus I effect. Okay, so also when you have see here you have a negative charge. Okay, so negative charge is more delocalized, so you have even lower stretching frequency. Okay, now the same case will be with the other systems also. See, you can see here the delocalization of the lone pair from ethoxy group to this carbon, and it can be delocalized further to this carbon. Okay, so the negative value, that means the change in the chemical shift. Okay, change in chemical shift is more here as compared to here. That means the effect of the lone pair of oxygen. Okay, whereas in this case it will be just the opposite. The carbonyl is electron withdrawn, so it withdraws electron density towards itself, hence this pi bond is delocalized towards the carbonyl, and also this is delocalized. So the earlier here it is negative, here it is positive. That means here it is shielded, whereas here it is deshielded. Right, it's deshielded. So also in the aromatic rings, okay, when you have the substituents with a lone pair, it can delocalize. Okay, it can delocalize towards the ring. Okay, so you can show the delocalization throughout the ring. Okay, but finally when you draw the resonance structure, you'll find that the para position and the ortho position, these are electron rich. Okay, or the electron density at the ortho. Okay, at the ortho, the para, okay, they are more, so the carbons will be shielded. Okay, whereas the carbon where the negative charge like is not going, so it will be deshielded. So you can have any substituent. You can have OH, you can have O minus, you can have NME2. Okay, and here will be the case where it will have the opposite effect. Electron withdrawing groups will withdraw electron density from the ring. Okay, from the ring. So here the ortho and para positions will be deshielded. So you can see here. Okay, will be deshielded also when you have a nitro group. Okay, Now again, another important factor is the charge systems. Okay, when you have the charge species, it can be positively charged or it can be negatively charged. The more the positive charge, the more will be the deshielding effect. Okay, so here the carbons are resonating at 207.2. That means that these carbons, okay, these carbons are resonating at 207.2. All will resonate at one field, so 207.2. Now in the cyclopropyl cation, 175 and here 155. So and here a neutral benzene ring, it will resonate at 125, 128.5 without any charge, only the pi electrons. Okay, but when you put a negative charge into the system, when you add electron into the system, that means that the electron cloud will be more, the electron density will be more. Okay, so the carbons of the ring will be shielded. Okay, so depending upon the charge of the species, it can be more or it can be less. Okay, depending upon the electron density. Okay, so generalization is, the more the positive charge, the more will be the deshielding effect. Then in case of carbonyls also, in the case of carbonyls, okay, you will see that the ketones are more deshielded as compared to aldehydes. Okay, let's see here the examples. Here you have a ketone, okay, where you have a CH3 here. Here you have a hydrogen. The other side remain same. This is same as this. But you can see here 206 for this carbonyl, okay, 201.4 for this carbonyl. Now here you have to compare a carbon and a hydrogen in terms of electronegativity. Okay, that means that carbon is more electronegative, it withdraws electron towards itself. Okay, so electrons are withdrawn from the carbonyl. Okay, the electron withdrawing effect of the carbon is greater than that of hydrogen because carbon is more electronegative. So the shielding effect for this carbonyl is more. So 206.3 and 201.4. Okay, but when you have electron donating groups, okay, when you have a methoxy group with a lone pair, it can delocalize its lone pair towards the carbonyl. So delocalization of the lone pair towards the carbonyl, that means you are increasing the electron density at the carbonyl. Increasing the electron density means you are shielding the carbonyl. So 173.3 will be the chemical shift. Okay. Now, when you compare this with the molecule here there is a delocalization of the pi bond towards the carbonyl. So delocalization will lower the stretching frequency in the case of the IR spectroscopy. So here also it lowers the chemical shift of the carbonyl. Okay, so from 206.3 to 197.5. Okay, so here also you compare this with this. Okay, so delocalization will lower the carbonyl chemical shift. Okay, here also. Okay, here from 173 to 166, or even in the nitriles, here you have a delocalization. Here you don't have the delocalization. Okay, and in these three examples, see the theta is shown here. Theta is 0, that means it's fully planar. Okay, here it's 28. Okay, so the planarity is distorted, and here it's 50. Okay, so the planarity here, it allows the delocalization of the pi bonds towards the carbonyl, free delocalization we can say. Okay, here because the planarity has been disturbed, so the delocalization is not as much as it is in the first case. Okay, so when the delocalization is restricted, so the chemical shift will be increased. Okay, that means here we can say that it's more shielded as compared to here. Okay, and here with the more substituents, here you have only one substituent, so the planarity, it's still there. Okay, it's still there, it has been disturbed to some extent, but here with the two substituents at the ortho positions, the steric factor is more, the steric crowding is more. That means that this carbonyl group has been twisted out of the plane by 50 degrees. So which means that more distortion in the planarity. More distortion in planarity means that the delocalization is very difficult here. Okay, so without the delocalization, the chemical shift of the carbonyl will be increased. Okay, so the carbonyl will show different chemical shift depending upon the delocalization, and delocalization here depends upon the steric factor. Okay, then here hydrogen bonding increase will increase the chemical shift of the carbonyl. Here there is no hydrogen bonding. Here the here we can see that the difference in chemical shift 191 187, mainly here it's because of the delocalization from the methoxy group towards the ring, towards the carbonyl, so it is lowered. Okay, but when you have hydrogen bonding, okay, when you have hydrogen bonding, the chemical shift is enhanced. The chemical shift is enhanced. That means when it used to delocalize, the negative charge used to sit here, but now the negative charge is being trapped by the proton. Okay, so polarization is not as high, it's not as high as it is when it is here, when it is free. Okay, the hydrogen bonding is so to say not allowing the negative charge to come to this oxygen freely, so this chemical shift is increased to 197.2. Okay, and here again, when you compare this with this ortho substituent and para substituent, in the para substituent there is more delocalization. Okay, more delocalization we can say, or we can also argue from the steric factor that when this is at the ortho position, then there is steric factor which we can say that delocalization. Okay, sorry. Now, when you compare here and here, the position of the methoxy group, here it is at the para position, it's delocalized. See, when it's delocalized, it goes here, then from here again comes here, goes like this. Okay, so as compared to here, the distance is more. Okay, so here the methoxy lone pair, it can be delocalized here, then to this bond, and then to this oxygen carbonyl. Okay, so the carbonyl here is having more electron density. Okay, as compared to here where there is no methoxy, but here it has traveled through this carbon, this carbon, this carbon, and finally it will delocalize. It will be delocalized towards the carbonyl. So 190.2. Okay, and here also when you have intramolecular hydrogen bonding, so the chemical shift of the carbonyl is increased. So the electronegativity effect. Okay, I think by now you can predict the chemical shift. of the simple molecule like shown here. Here you have four different carbons, because it's not symmetrical, so you can have A, B, C, D. Okay, so A, B, C, D, depending upon the type of carbon. Here this carbon is attached to an electronegative nitrogen atom, so this carbon is expected to be the most deshielded. Okay, the most deshielded, so you have C here. Then you have B. Okay, B proton. Then you have the proton C. Why? Compare A and D here. D proton is near to this carbon which has the electronegative atom. A, it's far from this carbon C which has the electronegative atom. So you can predict, as I've said, same like in the case of the proton NMR, the chemical shift will also be related depending upon the structure, depending upon the type of substituents. Okay, so what do you learn from the carbon 13 NMR spectroscopy is that you can predict the type of structure from the NMR spectrum, or you can predict the NMR spectrum from the type of structure. Okay, like as I've as I've told that when you see few number of signals as compared to the number of carbons, that means you can predict the molecule to be highly symmetrical. So the symmetry of the molecule can be predicted. Okay, like in this case you have 6 carbons but you have only one signal, so that means that you have a molecule which is highly symmetrical. Okay, but here see you have 17 signals. Okay, and if you count the number of carbons, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17, so that means that there is no symmetry at all. Okay, so the number of signals and the number of peaks, the number of carbons in the molecule, that you will be able to predict as to whether there is symmetry or not. Okay, like in this example there are 7 signals for 7 carbons. Here there are 3 signals, that means that you can predict the molecule to be symmetrical. Okay, you have this plane of symmetry, you have this plane of symmetry. It's not in, so you have one signal for this, another signal for this, another signal for this. Okay, this will be same as this will be same as this. That means you consider the plane and try to compare the environment. Okay, so like here also you can predict the molecule to have a plane of symmetry. Okay, that means this plane of symmetry, so you can count the number of carbons, 1 2 3 4 5 6 7. Okay, on the other side also, 1 2 3 4 5 6 7, so 7 signals. Okay, so like that you can predict a number of signals for any molecule. Okay, by looking at the symmetry. Okay, or from the number of peaks and the number of carbons in the formula, you can predict whether the molecule is symmetrical or not. Okay, see when you compare the proton NMR and the 13C NMR, now you'll find that the 13C NMR is much more simple, much more simple. Okay, see in 13C NMR, it's very difficult to predict about the number of protons here. It's not it. It can be written as multiplet, but when you come to the 13C NMR, there are specific number of peaks depending upon whether the molecular structure is symmetrical or not. If the molecule has some symmetry, that means the number of peaks will be lesser as compared to the number of carbon atoms. But if the number of carbons and the number of peaks are same, that means that the molecule is not symmetrical at all. Okay, so I'll give you like simple questions. Okay, like here I'll give you simple questions to predict the number of peaks in the 13C NMR spectrum. I know that for some it may be too simple, which you have learned in the master degree course, but for some you may need the basic concept. So the exercises or the practice which I will begin from time to time, it's for those who are interested. Okay, but remember that in the exam the questions will come from both a concept as well as the application. So it's up to you whether you read the uh, video which I'm giving, whether you watch or you don't watch, because when I check the YouTube link that I have given, I've seen that the number of views are much lesser as compared to the number of students. So which means that some students are not interested in watching the videos and all. But I'm telling you that the concept will be used in the prediction of structure. Okay, after you have learned about the 13C NMR concept, then we will go to the mass spectrometry, and then we will use the combination of all the spectroscopic analysis which we have done to finally predict the structure of the molecule. Then after that, then we'll go to the advanced NMR. Okay, and if you have any problem, if you have any doubt and all, you are welcome to interact with me. You can send me your doubts, or you can even call me for discussion.